let's record this, and there we go. So we're on the last bit of the statements about the fundamental theorem of Galois theory. Let me remind you, because I think it'd be good for the soul here. Let sigma in the Galois group of F over K and K in F. We say that A is stable relative to the Galois group if so this is what it means to be a stable intermediate extension. Let me take care to notice this does not mean that sigma E equals E for every E in there. All it means is stuff in E stays in E, right? It's like Vegas, right? But not necessarily that it fixes everything in E, right? And B, tau in the Galois group E over K is extendable to F. There exists sigma in the Galois group F, such that when you restrict sigma, you get tau. Right. So this is a automorphism on a larger domain that is exactly the original tau when you restrict the domain back down. Note, if tau is extendable, then E is stable relative to right, because notice that when you take sigma and restrict it down to E, you get the original tau, which is an automorphism of E. So you certainly get this condition right here. So here's a lemma here. If K and E and F are fields, then A, if is stable, then E prime, that is the Galois group of F over E, remember what E prime is, these are all the automorphisms of, these are all the automorphisms of F fixed E. So this is the Galois group of F over E is normal in Galois group. That ought to be fun to prove. And if H is normal, in Galois group of F over K, then H prime is a field, in fact, a stable intermediate extension. And of course, K okay, so let's go through this. First, I want to show that if E is stable, then the Galois group that is automorphisms fix E are normal in the automorphisms of F that fix K. So the first thing I'm going to do is I'm going to let U be an E and sigma be in the Galois group. And I'm going to have my little in the Galois group over E. And of course, my burden actually is to show that when I conjugate this tornado by the sigma, then it's still in the Galois group of F over E, right? Well, all right, I know this much. Every one of these crazy Greek letters is for sure an automorphism of F, right? So when I compose the three, I've got another automorphism of F. So really, my burden is just to show that this fixes everything in E, right? That's all I got to do is show that this automorphism of F fixes everything in E, right? Well, if you look at sigma inverse, sigma of U, well, U is an E, right? And sigma is, let's see here. So I got this. Let's turn around here. Right. Right. No, that's what I missed. Notice E is stable, right? And so that means that when I apply, so let me make a note of this before I get carried away. Since E is a stable extension, we know that sigma of U is still an element of E, correct? Because sigma applied to any E is an E, right? So if I look at sigma inverse, coordinate of sigma U, this bit is in E. And so this is sigma inverse sigma U. Because this because tornado fixes E, this is in E, so it leaves it alone. So now I've got sigma inverse sigma U, which is U. Therefore, so what I wanted, that is that the Galois group of F over E is normal in the Galois group of F over K. Okay, so far? Okay, now I'm going to nail down B. If H is normal in the Galois group of F over K, then H prime is a stable intermediate extension. Okay, well, we certainly have that H prime by our definition is an intermediate extension. So for part B, I'm going to let sigma be in the Galois group. Okay. course, I've got to show that this fixes anything in H prime. So basically, I've got to show that sigma V equals V to show the stability. Oh, I'm sorry. No. I need to show that sigma V is in H prime is what I need to show. Okay. So for all one over an H, we need to show that so that's all we have to do. Take an element of the Galois group, an element of H prime, and we need to show that when you apply sigma to V, it's still an H prime, which is equivalent to saying, what does it mean to be an H prime? It means that sigma V is actually fixed by any tornado in H. You okay, or are you just trying?
Yeah, I'm trying to think about like how I would do it. Sorry.
That's
why I was like staring.
You should never apologize for that. Okay. Note that after all, we do know that H is normal in G. We have that that's still an H. Right. Therefore, okay, so this is in H, and V is in H prime. So it's fixed by H, right? So and that's what we get. So actually, really, there's not much to this one except really sort of reinterpreting what we mean, reinterpreting our sort of need to show there. Okay, any questions? Okay, another lemma. If F is Galois over K and E is a stable intermediate extension, then E is Galois over K. Okay. Intermediate extension. E is Galois. Okay. The approach here, remember, one of the ways that we can show that E is Galois over K is to show that if there's something in E that's not in K, then there's an automorphism of E that moves it, right? That was one of our equivalent ways of doing it. So that is anything that's in E but is outside of K is moved by some automorphism of E. And that, of course, means that K would be the fixed field of this the set of automorphisms D over K. So to this end, U being E, but not K, Now, since F is Galois, okay. So notice, of course, U is in E, so it's in the bigger field F, and F is Galois. So there's a sigma in the Galois group of F over K such that sigma U is not equal to U. Everybody agree? So what we're saying is, okay, U is an element of E that's not in K. I need to find something that moves it, an automorphism of E that moves it. Now, maybe I don't know that immediately, but I do know that since F is Galois over K, there's an automorphism of F that moves it, right? But that is sigma U is still an E. So sigma restricted to E is in the Galois group E over K, and sigma restricted to E of U is not equal to U. So E is Galois. Yes.
I'm not understanding why that requires.
Oh, right, because the reason it requires stability is when I restrict this down to E, if sigma of E is not, if sigma E is not contained in E, this might fly off to some other extension. And then sigma restricted E is no longer an automorphism of E because it moved the stuff away from E, right?
Okay, so because we're,
right. Okay. Lemma, finally, 8-16. This sort of gives a bit of a converse to this. Let us suppose that K and E and F are fields and E is algebraic and Galois. Such that okay. Okay, then E is stable. So the previous lemma gave us, okay, if it's stable, then you get Galois. The partial converse we get to that is if E is algebraic and Galois, then it's stable. And this one, this is a very groovy lemma. And so I want to be careful with the proof here because it's going to illustrate something that's important about Galois theory that's not actually stated here. So let's go about this here. Proof. Let U be an element of E and F its minimal irreducible polynomial. I think I want to be monic too, just for convenience. Yeah, let's do Okay, so I know that the extension is algebraic, right? So if I select some u and e, then it's the root of some minimal polynomial. I'll make this polynomial monic. I don't have to, but it will be convenient. So let's list the distinct roots of f and e. Now, I know I've got at least one root of f and e, namely u itself, but maybe this polynomial spits out some other roots. So let me list these. U will be u1. And remember, my assumption is these are the distinct roots of f and e. And actually, I guess I listed R roots, so I'll stick with that notation in case to avoid confusing myself later. Notice that notice that the number of distinct roots is less than or equal to the degree of the polynomial f. There's a couple of reasons for that. One of the reasons is, for example, it could be that u is the only root and this f of x factors into x minus u, and then some irreducible polynomial degree n minus 1, right? Another thing, and you can generalize this, maybe it's got 3 roots and then it's got this big irreducible chunk, who knows? Or maybe the irreducible chunk breaks down into stuff that's not linear. And also, in theory, I mean, there's nothing stopping me so far. Turns out this can't happen, but we haven't seen that yet. The polynomial may have multiple roots, right? So for example, the root u may have a factor of x minus u cubed in there, right? Don't see any reason at this point why it doesn't have to be, but we'll get there. If tornado is in the Galois group of E over K, then it permutes the roots right? Because remember, that's one of the big things we learned about these automorphisms. Any automorphism of E must take a root of this. It must take U, which is a root of f of x, to some other root of f of x, right? And so if these are the distinct roots, it must permute these somehow, right? Maybe it's even the identity permutation, but it must permute the roots. Right? So what does that mean? So I'm going to build me a polynomial. I'm going to build this polynomial from scratch just by doing this. Now, if you apply any tornado in the Galois group V over K, what happens? Well, the x's are all left alone, right? That's the way we do these things. And the roots are permuted because they're all distinct, right? So Notice that, I mean, maybe U1 goes to itself, maybe U2 and U3 swap, and there's some kind of permutation, right? But there's actually a permutation, a one-to-one and onto function from the set U1, U2, U3 up to UR to itself. Every one of these does this. So, since each Galwan group and this is why another reason why it was important that I picked the distinct groups. All. Right? Because when I permute the roots, all I'm really doing is just permuting the product in there, right? This is actually, I think this is like a really slick proof, right? Because any permutation just turns these polynomials around. So that means that every element of the Galois group of E over K leaves this polynomial alone. Right? Since E is Galois over K, this implies the G of X in KX. Right? Because every coefficient of G, this polynomial is left alone under the influence of anything in the Galois group of E over K. That means that all its coefficients have to be in the fixed field. Well, the fixed field is exactly K because of the fact that E is Galois over K. So that means the G of X is in KX, right? And this is interesting because, so now we have G of X is in KX, and G of U is 0. So f of X divides G of X, because G of X is the minimal polynomial for you. How about that? But note the degree of G is less than or equal to the degree right? Because the degree of G is R, which is the number of distinct roots, which is less than or equal to n. Therefore, since they both lie, f of X equals G of X. So notice that all the roots of so notice that I sort of built my G there from scratch. My G of X is now equal to f of X. So what does this mean about f of X, or minimal polynomial for U? It looks exactly like this, and all the roots are distinct, So we got that. Remember, none of this repeated factor stuff, right? All words have to be distinct and they all lie in E. Therefore, E is stable. Because, of course, given any U and E, every place that you could go is also in E. And the proof of this is actually going to be used later. And I think this is amazing because basically, this is an important takeaway in this Galois extension. Our irreducible polynomial has to have distinct roots, right? That's important. We're going to talk about something called separability. And when we get to that, this thing will be kind of repeated. Okay, Jared's got and I actually caught somebody on the chat. How about that? What's your question, Jared?
Yeah, sorry. It's been erased, but I think it should be a pretty quick question. On the proof of 8.
I do have my sound turned on.
Can you hear me?
When we're on Zoom and we unmute to talk, you can't hear us here. I noticed that when I was.
Let me see if this is. Let me try this. Jared, you want to try to say something again?
Yeah. Can you hear me now?
Yes. Yeah.
Okay. Great. You've erased it, but I think this should be a pretty quick question. It was on the proof of 8.2.15. You took this sigma, which was an element of Galois f over k, and we just reduced it to being over E. And I understand that it has to keep everything in E, but I don't understand how we can guarantee that it's going to be onto when we restrict that element of Galois fk to just E. Like, I understand it has to remain in E and stay 1-to-1, but for an infinite set, how do we know that it's going to remain onto E just from the elements in E?
Actually, it does. Why don't you think about that, actually? Because remember, an automorphism has to have an inverse automorphism somewhere, right?
Okay.
And so you might think about what happens. So, you know, your sigma goes somewhere, and his concern is maybe it goes from E into E and maybe doesn't cover anything. But remember that automorphism has to have an inverse somewhere, right? In F in particular. And you might look at like what F inverse does to E. Right. In F, it's got an inverse automorphism, and you might look at what sigma inverse does. And I think you can get if it doesn't cover everything, I think you can get a contradiction.
Okay, thank you.
Does that help?
Yep.
Okay. Okay. And here we go. We've got lemmas coming out the wazoo today, but they keep wazooing. So here we go. So we got lemma, and this is kind of the final piece. And then I want to give you kind of a more general kind of party favor at the end of this, and then we'll talk about some other stuff. More cool stuff, of course. Lemma 8.2.17. Let K and E and F be fields with E stable. Then the Galois group of F over K mod the Galois group of F over E. Modulo F over E is isomorphic to the group of K automorphisms of E that are extendable to F. Automorphisms. E that are extendable to F. Okay, so let's do this one really quick, and then I'll also show how this ties together our last loose end or two. Define a function f from the Galois group of f over k to the Galois group of e over k by okay, again, here's it's math, better do something easy thing, right? I want to start with an automorphism of f that fixes k. Somehow I want to get out of this an automorphism of e that fixes k. So how about this? Just restrict it down to e. Now I know I'm going to be warm and fuzzy about this because e is stable, right? And so that guarantees the first worry I've got is, oh, look, I can certainly just restrict the domain down to E. That's no problemo. But then how do I know that this doesn't fly off into, you know, Missouri or something? And the reason is because of the fact that E is stable, right? Right. So the image of F in the Galwan group K is precisely, well, notice that the image comes from automorphisms of F in the first place. So the image of this is the subgroup consisting automorphisms E right? Because just by the very nature of the way this map works, this sigma restricted to E is certainly extendable. You extend it back to what it came from here. And notice if you have anything here that's extendable, then it certainly was in the image of this as well. Remains to observe that F equals the set of sigma restricted to E such that sigma restricted to E is the identity on E, which equals the Galois group, because these are precisely the automorphisms that are the automorphisms of F that fix E. Okay. So let me make a couple of remarks that I hope will kind of close this off and tell you this kind of final theorem here. So first, if E is an intermediate field that's Galois over K, then Galois group of F over E is normal in the Galois group of F over K. Now, since E and E prime are closed, which we established all that business earlier, and G prime is K, here where G Galois group. Reminder. We have G mod E prime, or the order of G mod E prime is the index. And remember, we can reprime these. Let's see if I get that right. Oh yeah, E double prime. Which should be EK. Because remember, E is closed, so E double prime is E, G prime is equal to K. So the order of the Galois, the order of this quotient group, G mod E prime, is equal to E over K. And so what we've shown is that G mod E prime I should say is isomorphic to the Galois group F of K. And this is isomorphic to a subgroup. The Galois group of E over K, of order precisely E over K. And so, since this is precisely of the right order, G mod E prime is isomorphic to the Galois of E, which is exactly what we want to show. Okay, so let me give a more general statement here to kind of conclude this section. So you might think about why this is true, and it's in slightly more generality, and I'll make this quick. Theorem 8.2. F is a field, G is a group of automorphisms. Automorphisms. F, that fix K, and K the fixed field. Then F is Galois over K. And if G is finite, then F is a finite dimensional Galois extension of K. With Galois group G. So you all now know how the correspondence works. We've gone over the proof of it. And we're going to talk about some other stuff, but we will eventually get our hands pretty dirty with looking at some of this stuff. Okay, any questions? Any questions? How about out there? Everybody okay for now? All right, well, y'all think about this and we will catch y'all next time.